Oh yeah, yes we do.
All right, everyone.
It's like 6 pages long. Come on now.
So, I have your attention now. I haven't graded it yet. Sorry. Need to get your attention. Mondays are not your best day, right? That's what I did on Sunday. Okay, class business, lots of class business. Whoever this was in here, if it's none of yours, I guess. The reason that you're the kind of guy who leaves your calculator is because you don't come to class. It'll be in the Lost and Found, so student Lost and Found at the student center. So anyway, or pick it up later. Let's see, so we're going to start grading the test tomorrow. I actually spent a bit of time over the weekend grading some sections because my TAs are badly overwhelmed. It's the largest class, smallest number of TAs ever. It's just how it happened. We just simply ran out of TAs available. So they're really kind of overburdened. That's why they make mistakes on your homework. We will make mistakes on your test. If you see those mistakes, come find us. Come by office hours and let me fix it, all right? I just implore you to do one thing. Most of the time when people come to me with a regrade, they actually got it wrong. So just to save both our times, just please look at the answer key. I did post the answer key, I think Saturday. I was a bit late. I had it written, obviously. It actually had a slight error, and I fixed it yesterday. Don't worry about it. It's not going to affect your test. So we're going to try to grade them tomorrow, getting them back to you Wednesday. However, I don't know that we're going to finish. I kind of doubt it. So it may be Friday, but that's as bad as it's going to get. It's funny. It's just that we're interviewing someone today and tomorrow, and it takes all my time. So sorry about that. So anyway, it does look pretty good. Maybe not as good as you think. I didn't think it was particularly an easy test, but you're a very good class. So for the most part, I saw pretty good scores. It heads up on two things. For one, when I return them, just like the homeworks, the scores on the back in case you don't want your buddies seeing exactly what you got in case it didn't go well. Also, and don't be trembling all day. When I have your test scores, if you did not pass, you'll get an email from me because I don't want you to be coming here and get to think that what? So anyway, so just if you don't want anybody to see what you got, I'll go back. And so don't be trembling all night, waiting, oh my God, am I going to get an email? Again, that's for your benefit. And if it really didn't go well, I'm going to say a little bit more about where you stand in the class, just so you know. And of course, you can come by office hours and look at your grades. And at some point, especially before the drop date, I'll make certain that you know all your grades. I'm not sure how I'm going to do that, but I will. Office hours, I just emailed you. I'm going to have to cancel tomorrow 12 to 1 because of the interview, so I'll do 11 to 12. Is anybody going to come by? Right, you don't even have the homework set. So, and I may cancel Wednesday too. So anyway, no one ever comes by office hours the day after a test. So that's obviously sensible. So anyway, so we're getting back to entropy. This is where things get a little bit harder. Before then, everybody okay? Any questions? We're doing all right, guys? There, yeah, look at them. There you are. All right. I like doing that. That's funny. Anybody have any questions, concerns? We're all set. We're all okay. All right. Yeah. All right. Let's just get into the material. Entropy. I didn't really have much entropy on the test because there wasn't much to say about it. We really just got into it. And you saw what you saw. So now we're going to get into more in depth on how to calculate entropy. And unfortunately, this is where it gets a little bit harder. And not only is entropy sometimes a little bit more difficult than you might think. I mean, I have equations for entropy, all right? So there you go. You use the equations. But we have inside entropy, we have outside entropy, we have the ways that entropies connect. With entropy, we're also going to do those last Legendre transforms. We're going to get Helmholtz energy and Gibbs energy. So that's where you've got all 12 of your equations in 4 conditions, right? So, anyway. Okay, so entropy is the change in heat over temperature. So don't forget that's going to be in units of joules per Kelvin, just like heat capacity. Oh, one thing, a lot of you messed up on the test. The unit section. Oh, CV is units of joules per K per mole. That's CV, comma, M, right? CV per mole. That's not the CV. Remember, CV is extensive. I simply express it in per mole because that's how you find it in a table. You have to multiply it by a number of moles. I only took off a point. Anyway, so the reason, there's more to it than just that. It happens to be joules per K. There's a lot that connects entropy to heat capacity. They are basically the same thing. So it's not accidental that they have the same units. Now, problem. Temperature is temperature, that's a number. Heat is path dependent. But I showed you that heat over temperature is not. So that means that we actually run into this bit of a weird problem where we have to force heat to not be path dependent. And we do that, this is kind of funky, you do that by choosing the path ahead of time. And we say it's a reversible path. So that's a unique path. There's only one reversible path among many paths, but only one is reversible. So that's how you can assure that entropy stays stays exact, and that makes it a state function. That means that it doesn't matter where it came from, it just is the entropy of my cats. I bought kitties on Saturday. Anyway, I'm going to show you. I know I'm super happy. I'll show you their picture at some point. The entropy of my cat, I have one cat, and then I have another cat, and now I have twice as much entropy, and that's again the state function. Now that I have two cats in the house, and things are kind of crazy because they're going, it doesn't matter how they got there. They're there, they're nuts, and that's how much entropy I have. And again, I started out with one nutty cat, and I doubled it by adding a second. So I can add it, and it doesn't matter where it came from. It just is. So that's, again, that's just statement of the state function. We've already gone over that. Okay, now, and again, all right, now here's the good thing. This is the part that kind of makes this easy. For the most part, it is easy. Is that entropy, being a state function, can be calculated via any path, right? It doesn't matter if I'm describing isothermal irreversible. I can calculate it adiabatically and reversibly. Because, why would I do that? Because it's easier. Why won't I choose the easier thing? Of course I'm going to choose the easiest thing possible. I'm going to choose the easiest path to calculate it. And it gets hairy in other places. All right, so let's do one of the formulas, right? So let's do the formulas. If I'm going to integrate these, delta S, the engineers are going to hold nuts on me. I know I'm bad about my calculus terminology. So this is formally correct. Now what is this? S initial, S final, heat, initial, heat, final, I guess. That's kind of weird. And again, I can choose any path. So why not isothermal irreversible? Well, that sucks. I'm not going to do it that way. Let's say we are isothermal and reversible. Okay, and again, I'm going to calculate the heat from this. Right, now it doesn't matter, again, it is irrelevant what I am describing. Cats in my apartment, the magic piston that's being heated and all that stuff or being worked on, it's irrelevant. I'm going to say that these are isothermal reversible cats. Okay, review. You just did it. All right, your joules. And therefore, the heat is, through the instinct, changing work. Okay, the changing work is, wait, I don't think I want to quite pull the cat out of this bag yet. Yeah, I'll tell you what, let me do it this way. So I'm going to do it reversibly. So I'm going to have minus work. I'm going to start there, minus work. And so that means that this is, okay, the IU pack, that crappy minus sign that they put on everything is now gone. Okay, but again, this is reversible. And remember, I don't use a subscript when I'm talking about the system pressure, so this is the internal pressure. Okay, and so remember, and I am missing the 1 over T, sorry. Jesus, that's horribly important. Okay, so again, I just replaced the reversible heat with minus the reversible work. Okay, and then I'm in the same situation I was before. nRT over T change in V, respect to under V. And of course, I'm going to start with the initial and the final. And this ends up being NR, LN, and I'm not, obviously, hopefully I've trained you well. I can train my cast to use a freaking order box. That 1 over x, integral 1 over x is natural log, so childish. This one I'm going to do a little bit. Okay. So let's do this. Okay, you know isothermal reversible, you know the work is minus n RT ln df over di. Because now you have that formula. You already have that formula. Hopefully it's stuck in your head. And remember, learn to derive these things. Don't try to stuff them into your head, although I just said that. You know that work is minus nRT ln df over di, and it's isothermal reversible. And it doesn't matter which way I do it, I get the same answer. So here you go. Life is cyclical. And in fact, you're going to do that several times. I'm going to have you re-derive the same formulas over and over again with different starting points, and you'll always get the same thing. So look out for that. Let's see, what else do I want to talk about? Okay, let's do heat. Okay. What have we got? Yes, I've been working out. Jesus. I didn't film that. So, okay, let's do entropy. Now let's do, all right, so I can see here that this looks good for expansion and compression. And that does look isothermal to me. I did specify that, but I can imagine if I heat something, and I think of entropy as like randomness. That's one of the definitions, and I'm going to be covering that here shortly. Entropy has many faces, right? We did Carnot entropy. Engines aren't perfect, that's entropy. And we're going to do entropy as randomness. That's kind of what we're doing now. I think a gas like a bunch of buzzing bees. So if those buzzing bees are buzzing more, I imagine that there's more entropy. And the way I inflame bees is I flame them, die. So if I heat something, it's just my gut tells me entropy is going to change. When I heat something in the box, everything changes. Why wouldn't entropy? And I'm not getting it from that. I don't see that telling me anything about temperature change. So that looks like an isothermal. And let's do a heat exchange. Now again, unfortunately, when it comes to heat, I have to just say I added 100 joules of heat by throwing this thing in the fireplace, whatever that thing is, magic piston the cat in the fireplace. All right, now what would let's take a metal box. All right, we'll have gas in the metal box. I'm going to add by magic reversibly 100 joules of heat. How do I get a number? All right, I'm going to tell you it's going to heat up 10 degrees. All right. The crazy metal box with the weird gas thrown in the fireplace adds 100 joules of heat. And, no, wait. Stupid today. Okay, the magic metal box with the magic gas is thrown in the fireplace and it gets hot by 10 degrees. Now give me energy. How do I get that? Huh? Come on. All right, remember? Heat capacity times the change in temperature, right? That's the number of joules. Now, it's in the metal box, there's no work, there's only heat. So I can take that change in temperature times heat capacity, and that tells me how many joules went into, in the case of kicking the fireplace, that tells me what the energy exchange was. Okay? Now I've got to integrate. This is word left. I'll integrate this, whatever, it doesn't matter. And this ends up being CV. And to train you well, I'll remind you that, of course, I'm going to give you per mole F over TI. Right, because again, I've got 1 over X, TI, TF. Okay, doesn't matter what you're taking, there you go. Okay, so there you go, that's for heat transaction. And in reality, let me just state that no matter what, delta S is NR ln dF over di. See, you can just add the two, and I'll explain why. Why you can just add the two, and you can always do it this way. In other words, calculate the change in S of the system. You can always work with this equation. No matter what question I throw at you, you can just write this down. It'll be on your cheat sheet, and you'll work it and you're set. Now, I mentioned that this seems to be the isothermal one. So you write this down and you work it. You're including an extra term. If this is isothermal, what is this?
Zero.
Right. So even if you've got your head up your ass essentially, and you don't know to not include this, it doesn't matter. It's not going to contribute, it's not going to alter your answer, and then you can be like, oh yeah, it's isothermal. If I heat a box and a gas and a box, and there's no volume change, then this automatically comes out zero. So you see, it doesn't matter how. See, just write this down and do it. And don't even think about it. And there you go, you got your answer. Now, foreshadow, OCD, foreshadow. Where it gets a little difficult is we're going to have to, I'm just going to get to this in about 10 minutes. Time's going slow. In about 10 minutes, we're going to have to start worrying about outside entropy and total entropy, the sum of the two. Unfortunately, it gets a little hairy there. As much as this is actually, this is nothing, right? This is nothing. Hopefully you saw the test wasn't hard, right? So the next test won't be that bad either. But when it comes to entropy exchange with the outside to get the total, it does actually add a layer of complication. All right, but before I get into that, I almost thought about not doing this. I want to introduce something and then come back to it later. Really just following the order of the book. I don't feel like this is necessarily the right time to bring this up, but I do want to follow the book. We are about 2 days behind on the calendar. And maybe there's some value in peppering you with like, hey, here it is, here it is, here it is, here it is, and then I actually use it. So I'm just going to stick with it. Okay, the Clausius inequality. There we go, that's a better cue. Clausius inequality. Clausius, I don't know what Clausius was. Jackass, I don't know. You should look him up. But Clausius, whenever you read about a lot of the older thermodynamics, this guy's name seems to pop up everywhere, so I probably should read something about it. But now, with Clausius inequality, when we come back to it, this is funny. This actually decides how everything works in the universe. No fooling. The Clausius inequality is that which decides how all chemical reactions and all processes work or don't work. This is like the most important thing I could ever show you. So it's not going to be quite obvious. And what we're going to do is relate heat to work. And as much as we did Carnot, right? Obviously we did Carnot. And the entropy, although it is hiding from us, entropy is why the Carnot cycle was not 100% efficient, unless, of course, the tailpipe's at 0 degrees, which it will never be. So that was entropy doing that, although entropy wasn't part of that calculation. We did show that the total entropy change was 0. That's fine, whatever. But what I want to do is, so entropy does dictate how heat talks to work. And that's one of the statements of the second law, which I'm getting into in a second. So to get the Clausius inequality, I want to relate heat to work. And because it doesn't matter how I do it, I'm going to say isothermal. Again, so one of the nice things, and I'll remember my units, about all this is that I can solve a problem by any means necessary. Of course, I'll leave that as it is. I'll leave that as it is. I don't need to, I was going to make it reversible. I don't need to make it reversible. In fact, I don't want to. So again, all these derivations, especially for this guy, I have infinite flexibility on how I choose to do it, because entropy, again, is a state function. Okay, now, let's look at this. I'm kind of blanking out because I'm trying to think of how to express this the best way I can. Okay, so now, with all those graphs, I proved this graph, but I didn't use any derivation, that the change in work is equal to the reversible change in work if the work was done reversibly. All right, so that's a trivial case. If not, remember that reversible work is the most negative, right? You got magnitude, which is the number, and then the sign. And that can be kind of funky. So when we're doing an expansion, that's negative work, and in that case, I know that this will be like -5 and that's going to be -3. That's absolutely true. Now remember, in compression work, compressions are positive because you're storing energy. It's positive to store energy. Remember that, all right? So in that case, this is a 5 and that's a 3, making this more negative even though it's positive than 5. So this still holds. And don't forget that you can treat these like equal signs, and it kind of is an equal sign. And you got this guy here. All right, so that's, again, childishly simple. Okay, now let's look back at this. All right, now, so what I want to do is I want to do the same relationship for heat, and this is the Clausius inequality, by the way. And what I'm going to do, I would like to ask you, what do you think I should do? But I think it would. Okay, so there's that. Now again, you know this is true. We've beaten this horse to death. I like hitting dead animals. And anyway, from that I can get this. And remember Jared in that South Park episode beating the horse to death in my head. So this is easy. This is all very easy. And I'm just saying, well, it's the same thing for heat, because if I choose to do this isothermally, then heat just does the opposite of work. So notice I just simply change which one is reversible. And it's absolutely true. And another way to put that I don't tend to do is do this. And so now I know entropy of the system minus the heat exchange greater than or equal to 0. And again, the equal sign is when the heat was exchanged reversibly. If it was not exchanged reversibly, then this is true, that the entropy change will be greater than the heat exchanged. And see, now again, you chemists, the engineers know this, you chemists you don't. Remember that in chemistry land, we very stupidly define heat as that exchange between system and surrounding only. And that's why adiabatic dQ is automatically 0, and that is correct. But it's not really correct. Remember, the problem there is that to say heat is only exchanged means that the inside isn't warm. It's like I wrapped it in glass wool, and then the inside suddenly went to 0 K. Well, that's crazy. That's not true. It still has heat energy. And because of that, that's where our definition of entropy up there is not really correct. The engineers always say it's heat, reversible heat over temperature plus a little question mark, plus what, the entropy generated? Engineers, am I saying that right? Yeah. Plus the entropy generated, which is basically a question mark, right? And that's what is that? That's the heat inside doing something. All right, so it does get confusing. Now in chemistry we are dogmatic, and we will only define it that way. And the engineers get this one, and this is a home run on their part, and they have the plus entropy generated. Now let me point out to you, okay, if this is the case, yeah, let me go ahead and talk about this. If this is the case, if this is absolutely true, as we're getting into, when we talk about reversible processes, that's when the total entropy changes 0, and in irreversible processes, the total entropy increases. All right, now, looking at this thing here, is it possible to have adiabatic irreversible? All right, because if I stick to this dogmatic definition, the heat in an adiabatic change is 0. And therefore, there's no entropy change. There's no entropy change to the outside because the outside is isolated from the system because it's wrapped in glass wool. And so there's no heat exchange. If there's no entropy change on the inside, then there's no entropy change at all. Right? That means there's no such thing as adiabatic irreversible. All right, so who thinks that there's such a thing as adiabatic irreversible? I'm too hungover. I get this far. So yeah, there is such a thing as adiabatic irreversible. God knows you've worked those horrible problems on the problem sets. But notice that our narrow definition in chemistry land says it doesn't exist, which is wrong. So anyway, just kind of fact points, you don't really need to know that. But there it is. And again, what is going to end up happening in the future is that this thing ends up defining whether something is spontaneous or not. And that is, does total entropy increase or stay the same, or does it not happen? In other words, this thing dictates all processes that occur. Two atoms collide and make a bond, a building falls over, the planet explodes, which would brighten my day somewhat. Anyway, so yeah, so let me go ahead and get into that part. I think you probably had a little bit of this in freshman, and I've not really been saying this about what is spontaneous and what is not spontaneous, what is equilibrium, what doesn't happen. So let me make a little chart. I think you kind of know this already. It's in your heart somewhere. Let's see. What do I want to say? So when it comes to working with cloud system quality, I have to stop now and diverge and talk about external and internal entropy. And so, let me write that down. System plus surroundings. Unfortunately, it's such a long word, equals total. And I'm talking about entropy, by the way. Okay, and so, if, let's say we're doing a reversible volume change, let's make a reversible, isothermal reversible. Okay, we gotta start thinking about heat exchanges and outside entropy and the total. Okay, in that case, the change in system entropy, and again, that's because, integrate, sorry, I know this drives some of you nuts when I don't do this. I already just went over this, NRLN, dF over DI. Okay, so there you go, I just did that a second ago. All right, now we gotta start thinking about what happens to the outside. Now there was a heat exchange, so the entropy of the outside has changed by our narrow dogmatic definition. So it works, all right? For the most part, that narrow dogmatic definition does work, except for A being irreversible, not there. Right? So, blah, blah, blah. Anyway, and again, remember, I don't use the subscript when I'm talking about the system. That's actually crucial to get that straight in case you had some problem with it. God knows what I want to say. Okay, now the system is this, and the surroundings. All right, delta S. How do I want to put this? Sorry guys, I hadn't thought this well enough through. If we're reversible, the definition of reversible, by the way, is delta S total is equal to 0. Now, again, units. I've always been bad about putting units myself. I shouldn't punish you for doing that. I only took a point off if you didn't have units on your answers, because I've graded some of them. Okay, if the total is 0, and this is the system, then you only have the surroundings left, right? So that means that the change, this is how I'll subscript surroundings, just obviously. That's obviously equal and opposite. dF over di. Okay, that's child's play. Right, so this is the one case that's kind of easy. Now again, remember, we got to think about systems and surroundings to get to the total, because the total entropy change is what decides whether something is spontaneous or not. Okay, so we have that. And again, that was to keep the total entropy change 0, because the total has to be 0 for the process to be reversible. If we're, okay, let's do isothermal irreversible. Okay, now this one is a headache, by the way. This one is really, really a headache. So the total is simply greater than 0. I won't put equal because that makes it reversible. It's simply greater than 0. So this is where this is a pain in the ass, because you're going to have it on your homework, you're going to have it on test 2. A gas expands, a gas contracts. Give me the entropy change of the system, surroundings, and total. Okay, total 0 in this case. Surroundings is minus that of the system. Irreversible, we write this. This is the answer. I guess I should start by this because it's one of those things that you have to memorize. But that means that the entropy change of the surroundings is unknowable to a limit. And this is the limit. And this, I have a really hard time remembering this. Is greater than minus that of the system. Oops, sorry, right, no, I'm an idiot. I say no subscript means that of the system. Sorry, I'm writing with a smaller and I said big S, better. Stands for who on my planet. But anyway, so this is all I can give you on this. And again, this is why this is kind of a little bit of a ridiculous pain in the rear end. I can't tell you, I can't definitively say this or this. Now, actually, what I was reading is, faculty, research faculty teach classes because I can keep you up on like the newest things that people are doing. There's this guy who's kind of getting famous for this. I forgot where he's at. He thinks that this can be defined, that therefore the total can be defined. It's irreversible in irreversible transitions, using something called the Jarzynski inequality, which is like, it's becoming the super famous thing in all the sciences right now. So I'm telling you right now, that these are the answers you have to give me, to be blunt, but it may could be true that you actually can't find the total and surrounding entropy change in an irreversible process. Some people believe this guy can figure this out. I don't think so personally, but I hate other people. So, okay, let's do adiabatic. Let's do irreversible. Now this one is actually easier. Okay, delta S of the system, NR ln VF over VI plus NCVM. Right? Notice that I don't even need my note, folks. So just to remind you that you can do this. You're going to have these equations on your cheat sheet. Okay? Now, delta S of the surroundings equal to, anyone want to guess? Huh? Zero. Why? Right. The no heat exchange. So in my very narrow definition, the only way the system talks to the surroundings is by heat exchange. Now, that's not quite totally true. A gas expands. Well, it just pushed out some volume of the atmosphere. So when the gas expands, the volume of the atmosphere, the surroundings, has slightly changed in a way that really doesn't freaking matter, right? So I'm going to determine entirely heat exchange. Okay, and then this is the same as the, with an S? Yeah, delta S meaning the system, right. The system, again, no subscript. Okay, so you see, we're building up layers of complication. Now let's do adiabatic reversible. Okay, now I've asked you a question on the test. And this is isothermal or adiabatic, whatever. Reversible. Give me Q, W, U, H, T, A, G. Oh God, it really is that bad. Give me total entropy change. Give me surrounding entropy change. Give me system entropy change. I said it's reversible. Write this down real quick. Delta S total is, right, there you go. Delta S total is 0. Now, delta S of the surroundings. Oh, sorry, units. Surroundings, what's its change? 0. And therefore, the change of the system is all 0. All 0, triple zeros. Ew, gosh. Cat ready to bite my feet like this morning. So there you go. Okay, now I promised you that, yes, the calculation of system entropy is relatively trivial. This is nothing. But, so you got these four conditions, and I am going to ask you about all of them, so you got to get this down. Now notice that I haven't even looking at my notes for like the test. I'm going to be like I'm a rambling idiot right now. But notice I can put them all up there. I didn't need notes. And remember, you had a cheat sheet. Even if you can't do what I'm doing now, which I would expect because I've been doing this 10 years and I have a freaking PhD, Dr. Physical Chemistry. So you have a cheat sheet. So you can do this. All right, now let me remind you again what everything is in terms of spontaneity. I have not been following my notes at all. Rambling like a moron. Talk about different processes and the change in total entropy. And I'll use a little, talk about maybe infinitesimal. So again, I'm trying to use some shorthand. Equilibrium. A process of equilibrium, whether system or surrounding, doesn't matter. What's the total entropy change? 0, right? It's very easy. Here, I'll cheat. Put it there. Then we have what you learned, what we call spontaneous. Our word spontaneous simply means, yes, this chemical reaction will occur. Because, I mean, this is chemistry. I'm going to talk about chemical reactions, which is what we're getting into. And when you were freshmen, you determined whether something was spontaneous or not. It just meant, does it happen, does it not? Okay, the total entropy change. Now, this can be irreversible. this. Most things are irreversible. Can I define the total entropy change? I can't, right? It's simply greater than 0. That's the limit of my ability to tell, unless that genius guy figures out the great formula, and whatever. Blah. Anyway. Okay, so that's how we define equilibrium and spontaneous. Okay, now what happens when total entropy change is negative? When you lose total entropy change, what kind of process is that? Huh? I've gone from, I heard the word positive, I heard, neither is helping. You can't add. Yeah, right. Does not occur. I just, look at that, really. Does not happen. Okay, and before we move on to another subject, I'm going to review a lot of things, and we've got plenty of time. Okay, so when you were a freshman in high school, freshman chemistry here, what did you calculate to determine whether a reaction occurred or not? Gibbs energy? Right, Gibbs energy had to be positive or negative? Negative. I just redefined it. I'm not talking about Gibbs energy. I haven't done that with Johnson transfer yet. I'm telling you that you said that Gibbs energy had to be negative and freshmen to be spontaneous. I'm saying something I think could be different, or maybe it's the same, that the total entropy has to be greater than 0. And as you've gotten older, and you've had breakups and all that, and you realize that life is completely insane, you probably realize that entropy, that I'm right. I am right. I'm always right. Yes. You probably have a gut feeling that this is correct. And I am correct on this. And delta G, so why did we tell you delta G was negative? Well, maybe that was the total entropy. Maybe. You just don't know that yet. I'm so kidding because I'm going to tell you tomorrow. So anyway. Okay, so I'm going to take another, today is kind of chaotic. I'm going to go off in another different direction before we get into delta G, because that's what's coming up. Delta G can actually be a little bit more of a pain in the ass than you thought. And let me summarize before I do that. Entropy has multiple faces. I'll put it this way. I'm just trying to think of how to express this. I think I probably should have prepared a little bit better. Okay, so when I ask you what are the 3 laws of thermodynamics, which is certainly an obvious question I'll ask at some point, entropy has multiple things. Right? First law, energy can be created or destroyed. The second law can be expressed so many ways. Can't turn all heat into work, pure work. It can't be done. All right, now we've learned total entropy determines spontaneous. Whether something is spontaneous or not, we'll start with my crude English shorthand. Determines whether something's spontaneous or not. And give me one of those two. But don't put both, by the way, because you might screw one of them up. Is a degree, this is the new one, of randomness. Okay, that's what I'm going to cover right now. But this is the hard part. This is actually what we cover in grad school. So I'm actually going to give you a graduate school level lecture, because I think you can hack it, and tell you about how entropy is randomness. I'm not going to hold your feet to the fire in terms of doing the calculations I'm going to do. I'm going to give you example calculations that are easy and give you an idea of why you go to grad school and why grad school can be kind of difficult. If you go into grad school in physical chemistry, you take a class on entropy called statistical mechanics. Statistical because you use statistics to analyze random events like lottery winnings and whatnot. Okay, so what we like to say is that entropy, not the change in entropy. Remember, I've been doing changes of entropy. That's all I wrote, changes of entropy. Now, entropy is a state function, so it has to have an equation, right? So remember when I said x dy plus y dx, the function is x times y. You can't have, if the change of a function is x dy, then there is, that's df, there is no f. I know I said entropy is a state function, is exact, and it does have a functional form. The problem is, it's monkey nuts. This is the craziest thing you're ever going to see. Well, let me introduce you slowly how this works. Come on, Henry, look at that, it's calligraphy. Let me introduce this very slowly. It's a function of this thing called, I'll call it rho, which is a degree of randomness. And I'm going to, normally I don't do this, but I'm going to go ahead and tell you, or number of microstates. Now, you go to grad school to learn what these things are. And it takes a long time to really get a hold of what these things really mean. Unfortunately, it is quite difficult. So I'm going to introduce you to the graduate level understanding of entropy, not the change in entropy, but entropy itself. And then there are example problems that you can figure out these things that are relatively simple. Because when it comes to things you do in grad school, well, there's a reason they're in grad school. Okay, so what I'm going to do is I'm going to have two boxes. I'm going to have two boxes inside glass wool. And I'm going to separate them. All right, so and then of course it's glass. The glass wool is important, or yes, it's adiabatic. It's just such that you understand the entropy change occurs not because of a heat transaction. This is going to be entropy change slowly done on the outside. And what we have are, let's say we have n/2 molecules in both, and let's say they're the same molecules, and then I have a degree of randomness on the left, and I have a certain degree of randomness on the right. There you go. And yeah, don't worry, I'm almost done. Now here's the crazy thing. As I mentioned to you before, entropy is a state function, and like energy, it has to add. So entropies, again, just like energies, entropies add together. So that means that the total entropy, entropy itself, which is a function of the left and right degrees of randomness or number of microstates, must be the sum. I'll call them both F. Trying to get my curves right. Okay, so they add together. That's brainless. Okay, but these things are like probabilities. We're going to analyze entropy as though it's a probability. Two flips of a coin each have 50-50 chances of being heads. What are the odds of two heads? 25%. How did you get that number? You multiply them. Multiply. What did you say happened? Same thing. Multiply one by half. That's the other. All right, so that means that it has to add. Oh, sorry. It has to add and simultaneously, be careful, add, multiply. So this is cool. I really like this part. This is why I want to introduce this to you, even though it's really appropriate for grad level. Okay. The total has to be the same whether I sum or multiply. How in monkey donkey heck can we do that? Any ideas? Can any of you think of a function that is the same whether it's added or multiplied together? Because there is one, and you know it quite well.
Natural log.
There's the number 2.
Logarithmic.
2 times 2. Okay, but what if the number of microstates is not 2? Then you've got a problem. Remember, it's a function. I'm looking for the function right now. I know that the function has its characteristics. Don't worry so much what you feed it. That's not so important. What function can be added or multiplied to get the same?
Natural log.
Yeah. And it was funny how you said it together. It's like, see, because you already know the answer, don't you? Or you just knew it. Oh, okay, I won't preach for you. So anyway, yes, natural log. Where do I have this? So yeah, natural log, row on the left. Now, natural logs, remember, they can't have units. So entropy has units of joules per K. And that would be the same as like the gas constant, except the gas constant is joules per K per mole. But if I have the gas constant as for a number of molecule, any of you know what that constant is?
Boltzmann.
Yeah, Boltzmann constant. Basically, you take 8.314 joules per K mole and get rid of the moles by dividing by Avogadro's number, and that's Boltzmann's constant. Kb. Sorry, what am I doing? R over Na. In case you weren't familiar. So I'm just going to multiply this by a constant, just because I need to give it units. Really, that's a little trivial, but I mean, well, it is what it is. And it happens to be true that this is the case. ln row left, row right, so they're multiplied. Right, so there you go. Okay, so I guess I have time for one example, and then I'll do another one later. I'll show you how to do example problems next time. Let me do one simple problem, and I'll let you go on time. Actually, I got a meeting right after this, so if any of you have questions, I'm sorry I can't answer. Hopefully you don't, we just had the test anyway. I do have to run right after this because we have a talk by the guy who wants to hopefully get a job here. Hopefully we'll hire him. So, okay, let's go back to the example of gases mixing and calculate the entropy change. This problem right here. Okay, so let's see. Let's define row left is okay. So when it comes to the number of microstates, the damnedest thing is that the way to think about the degree of randomness, the thing you go to grad school for is to understand how to get what rho is. And so I can't really tell you how to do this because it takes an entire year of graduate school. But I can look at this, and because I went to grad school, I know that it's actually a half. Because a gas molecule had the probability of being on the left was a half. That's what it comes down to. And of course, I have n to the 1/2 of them. I'll do it like this. Okay, now again, I know this is out of nowhere, but I can assure you that the degree of randomness, the number of microstates, happens to be 1/2 in this case. Again, because those gas molecules on the left happen to be, there was 50-50 probability that they were there. And that's the same as the ones on the right, obviously. Nature doesn't move left and right. 1/2, 1/2. Okay, now this is before. Before what? Before I lift the partition between the two and let the gases mix. So this is the entropy of gases mixing. Okay, so it turns out that after row, now I know this is going to be a little confusing. There is no left and right after I remove the partition and let the gases mix. So I don't have two rows, I've just got one. Now, okay, again, I hope this doesn't rattle your cage. I happen to know that the number of microstates after the partition has lifted and the two gases have mixed is the number 1. Why? Because there's only one way for the gases to have mixed. I hope that's not okay, yeah, it kind of makes sense. I hope so. It's the best I can do. So that means that the change in entropy is going to be Kb, and I'm looking up here. It's not a good way to put it. Kb ln. Yeah, I can do this. Row left, row right. And that is equal to Kb ln 1 over row left and row right. Right. Yeah. That's correct. Sorry, I was kind of blanking out because I'm kind of doing this off the top of my head. Okay. Now, what does that mean? What does that equal? Okay. Yeah, I'm out of time. Is that thing going to beep? Did I just hear that? Or maybe one of your phones. Anyway, okay, that's fine. Because I'm out of time. Kb ln 2 to the n. All right. So, yeah, 2 to the n. Yeah, that works. All right, so then that ends up being n Kb ln of 2. Okay, there you go. All right, so anyway, with the statistical mechanical definition of microstates, which again, you have to do a graph, and I know it's on the record, knowing these things, I can then calculate the difference before and after lifting the partition, and I get this. Now, my point is that you can do a gas doubling in volume, and the way that works is the number of moles, let me think here, NKB, natural log, VF over VI. Okay, so when we talk about the change that has just happened, because this is basically the same as NR. So what I've done is I've taken moles times the gas constant times the number of molecules times the Boltzmann's constant. And this ends up being NKB ln2. Because from each gas side's perspective, the volume just doubled. Right? So they're perfect gases. The gas on the left don't see the gas on the right. Remember, the perfect gases, they fly right through each other. So as far as the gas on either side is concerned, the volume has doubled. These are the same. This is the formula I gave you just a few minutes ago. And this is the wacky natural log formula, but they end up being exactly the same. So there you go. All right, so I've gone way over, and we'll do a little bit more of this. I'm not going to really hold you too much for this, but I do want you to see how this stuff actually works. Remember office hour change, I'll just see you on Wednesday.
Except he did it with way more than just 2 mistakes. Yeah. Exactly.
Some of every state.
Yeah, his shit was crazy. I got completely lost in that class. Everyone was easy. Like, yeah, he started working.